So, good evening and good morning, wherever you may be. Welcome to this CRE talk number 55. Today, we have the pleasure of listening to Dr. Pramod Kulkarni, who is a retired Commodore with the Indian Navy. He has spent more than 38 years with the Indian Navy. He has also done his PhD from IIT Delhi and more recently has been looking at publishing his work in the form of a book. And currently he is the Pro Vice Chancellor at Reva University in Bangalore, trying to bring a design program into that university and set up probably a design program on engineering design in Reva University. With this brief background, let me invite Dr. Pramod Kulkarni to share his views on the talk is titled Evolution of Warships, Design History of Over 1,000 Years. So over to you, Dr. Kulkarni.
Thank you, Dr. Varatharajan. I wanted to confirm if the screen is visible and the presentation is visible.
Yes.
Okay. Good evening to you. I'm talking from Indian Standard Time, and thank you very much, Dr. Varatharajan and the forum for this privilege. The topic today that I'm going to be presenting is the evolution of warships design and the design history over the last 1,000 years. The objective is, the motivation is that the designer needs to acquire this perspective because it simulates the design thinking, particularly when one is contemplating the development of the next generation design. This kind of design history is not normally associated with any product. Architects do it. They study the history of their buildings. But when it's coming to the products, it normally doesn't find itself in the curriculum. So the history of cars design or history of, so this kind of a thing. So that's what I thought, since I have been a career in warships design, I thought it, an interesting thing to compile this kind of a history. If you look at the technology of naval warfare, though it's been over 2,000 years that man has been fighting war at sea, after the stabilization of the sail and the associated technologies of seafaring, the technology and tactics of naval warfare were pretty stable for over 200 to 250 years. You can see the chronology over here in yellow. So between 1600 to 1800s, the technology was rather stable. And thereafter, around 1820s, 1830s, the Industrial Revolution came in. And this saw a very rapid and fundamental changes in the capabilities of the warship, injected because of its design. And the outcome was the tactics of naval battle changed every 10 to 15 years. And what was the range over which that warships could engage was about 3 nautical miles around 1850. And within about 150 years, the range over which warships could engage in battle increased from 3 nautical miles to 3,000 nautical miles. And in the 25 years since the year 2000, this has increased to about 5,000 nautical miles. So you can see the impact of the technology and impact of injection of that technology into the design that has brought in this capability into the warships and the fleet. So this is the journey that I'm trying to be capturing to present over here. The catalysts for this evolution in warships design have been primarily the Western imperialism and their expanding empires, which saw the investments into the warships design. The Cold War, after the imperialism, the competition between the superpowers has also resulted in very innovative designs of warships coming out. The rise of nations, there's a very strong correlation between the rise of nations and the rise of their navies, because navies are very costly, amongst the armed forces, the most costly fleet in terms of demands on the money. And the maritime doctrines of different nations have been different. So that has also contributed to the evolutions of designs and evolutions in different directions. So these have been broadly, I'm going to be stitching them all together as I'm going to be proceeding here. There's been power supply drop, but I'm sure it will return back. The scope I'm going to be covering is the technology management in the new product development, nothing to do with warships, but overall, and then trace the evolution of the modern warships history, the interplay between naval technology and naval architecture, and the impact that this evolution has had on the transformation capabilities of warships, emergence of new classes of warships, and extinction of some of them, like the dinosaurs have become extinct, and its impact on the tactics of naval warfare and its impact on today's warship design. And I shall conclude by giving an overview of the drivers of this evolution and the takeaways for the design. The motivation originated from the design manifesto that was promulgated by the MHRD, the Ministry of Human Resource Development, which was wanting to inject a design spine into every engineer who is produced in the country. And the second was the gap area that existed, that we don't have any resource book to support the education of warship design. And that's when I conceptualized the need to author a book on this subject with a textbook writing grant from IIT Delhi. And the outcome is that I've got a book which is about to get published. So this particular topic that I'm presenting today happens to be one chapter in the book. The technology life cycle, a well-known one, that from the emerging technology, the product, it grows and matures, and thereafter it reaches its end of technology life cycle, end of product life cycle, when it starts becoming obsolete. So the curve on the right hand side shows that no matter how much is the increase in the developmental effort, the product's performance reaches an upward plateau or an upper ceiling, and you are not going to be able to extract any increase in the product performance, no matter how much is the increased developmental effort. In order for you to break this ceiling, you are required to invoke the emerging technology and the disruptive technology, start a new S curve, and then with appropriate injections in R&D and and then write the next S curve. So this is what is going to be the feature that we are going to be seeing when we are trying to map the evolution over 1,000 years, and how one S curve has been replaced by the next S curve, and then how the subsequent S curve has followed. Beginning with the story of the evolution, on the bottom is the chronology, and the seafaring required the compass, the sextant, and the chronometers, technology that stabilized. It took 300 years to stabilize, and that is how, in spite of all this technology being available for over 300 years, it was only in a space of just 2 years that 8 years, that Vasco da Gama and Columbus embarked upon their very famous historic journeys, when they integrated all these things and the technology of seafaring stabilized. In those days, there were no pirates. Sorry, there were no navies, and the riches of the from the Spanish colonies in the South Americas, when they were bringing back the riches, the poorer countries like the UK, Britain, used to commission the pirates. And the pirate ships had the design characteristics of being seaworthy, rugged, agile, highly maneuverable, well-armed, and were designed to intimidate their prey into surrender. So that is how, when the gun ports were invented, on that, used to have these gun ports as shown over here. The cannons used to be mounted over there, and they would quickly strike without warning. This was primarily how the precursors to the warships were the pirate ships. Subsequently, the ships evolved, and they came to be known as what are known as the ships of the line. And the ships of the line, the tactics was that the fleets fought in line side on to the enemy, packed the ship with soldiers, and boarded the ship after damaging the hull and the mast. And all this was done by the cannons. The ships were so heavily armed that they used to be called the first rate, second rate, third rate, and the fourth rate. Even today, when you want to represent or reprimand somebody or talk about demeaning way that something is not good enough, you say it's a third rate stuff. So this originates from the names of the ships. And the first rate ships had over 100 cannons. And to put this into context, the Napoleon's army in the Battle of Waterloo had only 70 cannons. So you can imagine how well armed these ships were. But the problem was that even though they had about 80 to 100 cannons, only half of them could be brought to bear in a battle. And because either they were on the port side or the starboard side, or the left side or the right side, is what these guns could be brought into bear in the battle at any time. So these were primarily the type of ships during the sailing era. The carracks and the galleons were used by the Spanish and the Portuguese. The pirate ships, the brigantine, which I talked about. The French standardized their frigate design in around 1800s. And at the right side, you see the classic ship of the line, the guns over 3 decks, about 100 cannons in them. All of these changed when the Industrial Revolution kicked in. And there have been about a dozen technological milestones that have impacted the warships design from the journey from 1850 to about 2000 or 2025. I'll be taking you through these milestones. The changes have been so rapid in the first 50 years that the sail gave it to steam. Iron and steel superseded wood as the material. Guns moved from lower decks to the upper deck. We saw the guns were all on below decks. High explosive shells replaced the cannonballs. The fighting range increased from 300 to 400 meters to 20 nautical miles. And the fleet, most of the battles were fought very close to the coast. They became a blue water combat force. And all of this transition happened in just 50 years. The contributors were the steam engine. In 1820, we had the unreliable steam engines combined with the paddle wheels. Subsequently, in 1840, the screw propeller was invented. The steam engine got refined. And that is when the capability that didn't exist before emerged, that is maneuver independent of wind. And because of this new capability and new tech, it was quickly adopted. It completely transformed the fleet and the tactics. And what it did was it made all the existing ships obsolete. So we are going to be seeing this many times in this journey downstream, that overnight or at a very short period of time, the existing things suddenly become obsolete. Similarly, the naval artillery underwent revolutionary changes. The gun barrel improved metallurgy resulted in an ability to withstand higher pressures. Machining technology came in, so they were able to machine the internal grooves, where they called the rifling, which imparted a spin to the shell that gave it stability, directional stability, and longer range. The shells, which are primarily like stones, or they were packed with chemical propellants, which were able to drive the shell further. So the same weight was able to have 3 times greater impact. And similarly, the aiming technologies also from the naked gun, the telescopic sight came in. So outcome of all of these enabling technologies or integrating all of these things together resulted in doubling the muzzle velocity, higher striking range, and smaller dispersion. And this wood could not resist the smashing power of this rifled ordnance. And wooden battleships became extremely vulnerable and obsolete. So now something had to be done to survive in battle. And that is when the antidote to these explosive shells came in the form of iron armor. So initially, these wooden hulls were coated and plated with iron around them. Subsequently, the improvement, and these came to be called as ironclads. Subsequently, the steel making emerged. Steels always used to be made in our history. You must have heard the Damascus swords, and swords used to be made of steel. But at an industrial scale, which is required for making ships, the smelting technology and the metallurgy and the large-scale industrial steel making emerged. That is when the armor was possible to be made in larger numbers, in quantities. And the wooden ships began to be cladded with armor. So they began to be called as armor clads. So this is one of the pictures of an armor clad. And what it enabled is that it ushered in an era of ability to wage battle at sea. The gun ports could be, located higher, and they could be, go out in rough weather and still fight the battle, because the gun ports could be, armor was light. It was enabled them, the guns, to be mounted higher. Steam completely changed the tactics, but the next milestone was fuel dependence. The sail ships used to be out at sea for up to 6 months at a time. They didn't require any refueling or, independent of any need to be connected to land other than the food and water. But the steam completely changed the tactics because they enabled the maneuver independent of wind, but the fleet's endurance came to be determined by its ability to carry the fuel or the fuel supply. So the coaling stations became important, and from that day onwards, the geopolitics and the coaling stations and subsequently coaling stations, the need for naval bases around the globe became a part of the geopolitics. The second thing it did is that it introduced the concepts of strategic mobility and tactical mobility. Strategic mobility is the ability for you to be away from the base port for long, how long you can be. And tactical mobility is that in the battle, how much maneuverable you are. And the designers, ever since that day, trade off one for the other. They trade off speed and for the endurance. And this is something that from that day almost to warships of today always balance one for the other. The solution for the strategic mobility resulted in a new class of warships coming in, and that a new class of ships coming in called the fleet tanker. So that is how the fleet tanker emerged on the scene. There's a very important case study of a design disaster. The map, I do not know, it's a very small looking, but this is an area which is a flashpoint of geopolitics today. That's the Crimea. So though today they are fighting over Crimea between Ukraine and Russia, but the first original battle for Crimea took place called the Crimean Wars between 1853 and 1856. And during that time, there was a very innovative British captain called Captain Cole, who learning from the railways were that time coming up into the of age, and when the railway train came in, it was a problem to actually reverse the train. So they came up with a turntable wherein the engine could be mounted on a turntable, and 4 people below could turn the table and then turn the engine by 180 degrees, and so the engine was able to be reversed. So he got the idea from there and patented this methodology of, instead of the engine, train engine, he placed a cannon over there. So this is when the swiveling cannon came about, and he was able to have the cannon placed in a rotating table mounted on a barge, was able to cover a much larger firing angle. And this design proved to be was quite successful when placed on a barge during the Crimean War. So Captain Cole was a very influential and a charismatic person, well connected in the British hierarchy, and he went on to become the member of the British Parliament. And he influenced the design of a new generation of a warship, wherein he placed this rotating cannon on a warship, and he called this HMS Captain. The chief naval designer, Edward Reed, opposed this design, and he went on to resign in opposition to this particular design, because this was sanctioned by the British Parliament without approval of the naval designer. This ship, in her maiden voyage, just outside the harbor, she sank, and all the people on board lost their lives, including Captain Cole, because primarily that the sails were still there, but below the sail they had mounted the guns, and it didn't really, the design was very nice, much forward, revolutionary at that time, but it didn't succeed. This is was a turning point, because this is the time when they found that you can't be leaving design of warships to amateurs, and it can't be somebody's fancy idea that it can go to. And that is when it was recognized that warship is a design as a science and as a professional discipline was recognized. It was recognized that designing a warship with iron, steam, steel, large guns, and armor was very different from past methods. Propellers and marine engineering and hydrodynamics and propeller design required it to be a specialist discipline. So the British at that point in time, very pioneering people, William Froude, we all know in hydrodynamics, his Froude number is something that we still use, came up with the first towing tank. In the design of the propeller, Charles Parson discovered that his propeller was not achieving the required speed. He discovered the phenomena of cavitation, and he was the inventor of the first cavitation tunnel, which we still continue to use today. But the credit of really bringing this as a professional discipline goes to the French, who call their specialist course called the Génie Maritime. And learning from them, the British started a professional corps of designers called the Corps of Naval Constructors. So this was a very important turning point in the design of warships, and which even today we are talking of how to train our designers. So this was something that we can study. The story about rotating armored turrets, that was a very good important experiment. You can see the pirate ships, you can see the HMS Captain. During the American Civil War, they built, the turret was brought on top with the armored turret, but it was centerline mounting, caused a lot of low freeboard, a lot of capsizing, because it interfered with sails as well. So therefore, for this to happen, 3 technological developments were necessary. The era of sail would have to end. The guns would have to be required in smaller numbers. You can't afford to have 50, 60, 100 guns. You need smaller number of guns, and the armor would have to become even more lighter. And all these three things happened in the next 10 to 15 years. And the masts and broadsides is the guns mounted on the sides, disappeared, and they were replaced by smokestacks. Smokestacks were the funnels because of steam engines, and the turrets. The turrets is what came up where the guns came on the upper deck. So if you see the bottom of the slide, from 1880 onwards was the early steam navy. And the battle tactics required a ship that was capable of long range action, independent of this fleet, and someone who could keep an eye on the enemy at a distance and still escape if he's pursued. So you required someone with the capability of long sea legs. The propulsion plant became reliable, powerful. Improvement in armor technology resulted in high-speed steaming capability. And a new capability emerged that didn't exist before, that is wireless telegraph. So for the first time, the fleet had an ability to have real-time reconnaissance from far beyond the limits of the horizon. And after he has sighted something, he didn't have to sail back and tell the fleet commander about it. He could tell from there using the wireless telegraph about whatever he has seen and observed over there. This is a technology that's crucial even today. And these were all injected into a new class of vessels called the cruiser. Cruiser is basically a ship that can be out at sea for long, cruise for long. So these cruisers were given need to be large because they had to carry a lot of fuel, so that they can be away from the base port for long. So emergence of a cruiser capable of protracted voyage is what emerged. And by around 1900s, these were the largest ships in the fleet. And look at the period of 1900. The Wright brothers had still not yet invented the flying machine. And subsequently, when the flying machine came in, the aeroplanes came in, and they had to be integrated on the ships. And what we now today call the aircraft carriers, it is these cruisers, because of their size, became the first ones to be converted into aircraft carriers subsequently. This is how the order of battle was. The range over which the guns could engage, the fleets could engage, from about 300 meters, it has now become 3 nautical miles. That revolutionary new weapon was invented called the torpedo. And why it was revolutionary was that it could be fired from a small vessel and still could sink a capital ship. And this is why it was patronized by nations with limited means to build a large fleet, particularly countries like Germany. And later on, this weapon became a weapon of choice for 2 new types of warfare that was to emerge: the submarines as well as naval aviation. And because of this new weapon system, the design changed, and then the new types of ships came up. 2 new types of ships, class of ships. One was the torpedo boat, and second one was the torpedo boat destroyer. So this is the tactics used by the ships. Navies did not have very large ships. They used these small vessels fitted with torpedoes, as shown over here. And the tactics was to approach at high speeds, deliver the torpedo, and run away. And these could sink the capital ships of the enemy. The shortcomings was that they had to be small because they had to evade the gunfire. They had to come within the range of the enemy's guns, and because of that small height they had about what we call the freeboard, they had very poor sea keeping, and they could threaten only in the coastal waters. The bottom left picture of a torpedo boat, and if you see if you study the ongoing battle in Ukraine and Russia, the Ukraine has used autonomous vessels to target the Russian ships, using boats very similar to like this, what you see on the bottom left. So you can see the history repeating itself, the same kind of a design emerging with different kind of a weapon system. Now these torpedoes were immense, and ships with navies with very big capital ships like UK had to counter these torpedo boats. So they came up with light, quick firing guns that required a number of inventions and integrating of them into the design, which today we know they've evolved into close-in weapon systems. So these got incorporated into the torpedo boat destroyers. They got different names: torpedo catchers, torpedo gunboats, torpedo boat destroyers. But ultimately, all the prefixes got dropped out, and these vessels came to be known as the destroyers. So today, when you hear the destroyer, it owes its history to the torpedo boat destroyer. The characteristics, design characteristics were they have to be as fast as the torpedo boat, but carry much more firepower. Only then they could destroy the torpedo boat. The steam engine had reached its upper limit of that S-curve of performance I told you, because these vessels with the thicker armor, bigger guns, heavier warships required more and more power. So the more and more power was possible only with a larger diameter and larger piston stroke. So you can see the height of these, the size of these engines. They become bigger and bigger and taller and taller. And when they were incorporated into the ship, on the left hand side, you can see the picture. That is what decided the height of the ship. We call the freeboard. So they became tall ships. And moment you have got a tall ship on the water, you become an easy target for the enemy to hit at you. So it was not a tactically user-friendly profile the ships were getting because of the steam engine. So the steam engines were reaching the upper limit of what technology was capable of. And that is when the steam turbine got invented. And the steam turbine was compact. It did not have the disadvantage of increased height. And what it resulted in is the warship that could sit close to the water. And this revolutionized the warship's design because of the efficiency it brought in, the weight saving it brought in. And the weight saving was possible to be invested in the lower silhouette as well as in the increased firepower. So around that time, around 1900s, the technologies were all in place, but they required to get integrated into one ship. So that is what happened, and the outcome was a design called the HMS Dreadnought. And this was a leap in transformation in warship design. And this design eclipsed all the earlier designs and made all the frontline ships obsolete in one stroke. What it did was that it did away with all the small guns and just had about 5 big guns. It was all turbine powered. This is the first warship with steam turbines. And it was heavily armored battleship. The other feature that it incorporated was that all these 5 guns were integrated. And this is when systems integration took root for the first time. All the 12 guns mounted, or the 5 guns with twin guns, all the 12-inch guns mounted in 5 turrets were calibrated to a common reference, and they functioned as a single system. And this integrated central fire control system gave the ship twice the firing range of the pre-dreadnoughts, or the ships that did not have this kind of an integrated systems integration. So this was a big leap, and it made every other battleship obsolete overnight. It revolutionized naval power, and it was so path-breaking that all the subsequent battleships came to be known by this name, dreadnoughts. And all the ships of the previous era, they came to be called as the pre-dreadnoughts. And the design of this ship, even modern warship, is, owes its lineage to the design of the HMS Dreadnought. This is how the order of battle was. You can see that the main guns with the range of 6 to 12 miles was that now. You had the Germans launching the torpedo boat assault against these capital ships, and you had a screen of destroyer torpedo boat defense against these torpedo boats. So this is how the World War I naval battles were fought, with torpedo boats, torpedo boat destroyers, and of course the dreadnoughts. The Germans developed the destroyer as an offensive weapon because they didn't have the ability to build the fleet like the British had. But the British developed the destroyer as a defensive weapon to target the torpedo boats. But either way, the design approach is changed, where the thought process has changed, the tactics of the maritime thought changed, and this is what contributed to evolution of the destroyer. The problem of poor seakeeping and endurance was overcome, and the outcome is that every naval battle, whether it's World War I, World War II, and even today, the destroyer has evolved from a 200-ton coastal vessel in the early 1900s into 6,000 to 8,000-ton highly capable state-of-the-art warships today. And the outcome is that the destroyers have the distinction of being the largest number of warships produced in the history. And they still continue to be there in the front line. Going back to the dreadnoughts evolved. They became, there was frenzied naval arms race between competing imperial powers of US, Britain, Japan, and Germany. The bar was repeatedly raised with faster and more powerful ships. They were called now not the dreadnoughts, they were called the super dreadnoughts. They were large, powerful guns, heavy armor, underwater protection, high speed, very good cruising radius, seaworthiness, but coupled with a very important capability capable of being absorbing very heavy damage in the event of a battle and still continue to fight. So they were hulks floating and roaming the seas. Their guns became heavier from 12-inch to 14-inch to 16-inch caliber, improved fire control, and what it did is they were able to fire accurately up to the horizon. Horizon is typically 23 nautical miles. And even when they were maneuvering and the enemy was maneuvering. So this was how the technologies came in. At the end of World War I, the countries became bankrupt. And that is when, for the first time, the powers of that time, they entered into a treaty. This is the first arms limitation treaty. And what was discussed on the table was the product called the warship. And the warship's design was a subject of this treaty. So the 5 power nations came up together saying that let us stop building bigger and bigger ships, and they came to the treaty that we will not exceed the gun caliber to more than 16 inches, and we will upper limit of our designs of our ships shall not exceed 35,000 tons. And the outcome of this treaty was 26 American, 24 British, and 16 Japanese warships had to be scrapped. But unfortunately, this treaty remained in force only till mid-1930s, till a gentleman called Adolf Hitler came on the scene. And then the World War II came in. And when the treaty limitations were broken, bigger and bigger battleships and bigger super dreadnoughts emerged. This is the biggest dreadnought, the biggest battleship that was built, designed and built. This is the Japanese IJN, Imperial Japanese Navy Yamamoto, 72,000 ton displacement. And you can see the beam of 38.9 meters. That is 3 modern warships can side by side, if you place them, that would be the beam of this ship. It's not the 3 guns in 1 turret, and you can see it was a really huge ship. This is how the order of battle was. You had the main battery of the dreadnoughts and super dreadnoughts continued to be the gun. The carrier had emerged. The flying, it had now become a 3 medium combat. 3 medium combat is the submarines with the water, the aviation, and of course the surface navy. But you see the aircraft carrier here, you can see the bottom right is behind the dreadnoughts. It is basically providing you air cover. It is not an offensive weapon. And you still have the dreadnoughts are protected by a destroyer screen. I talked to you about how the destroyers were there to protect against the torpedo boats. So this is how the 3 medium combat came in just after the World War I or around that time. Though I can end the case study of a battleship, but I'll still talk about one more. This is the Bismarck. Why this is special is this was Hitler's favorite ship and my favorite ship as well. Now you look at the top Bismarck, you see where the paint and how it has been painted. A false bow wave has been painted to fool the enemy from his visual sights when seen through the binocular, to make the ship much smaller than what it actually is. So this is how stealth took place, or this is how they were trying to, stealth was used to kind of fool the enemy. The second aspect about this design is that if you can see in the center over here is a rail, and through this rail, aircraft used to be launched, and so an aircraft was integrated in this design. So we talk about integrating different things into the design. So this ship had aircraft could be launched. It was not an aircraft carrier. It was there, and then it was a one-way street. The aircraft could take off, but it had to be ditched, and they had this huge, long, huge crane which had to be, would winch the aircraft out and back on the ship. The fleet air power became more mature, rose up this S-curve, and the Japanese were leading this naval aviation, and they had the most reliable aerial torpedo. They had the most robust fighter-based carrier-based fighter called the Mitsubishi A6M, which is very famously called the Zeros, and they had the bomber, the Kate bomber, nicknamed as Kate, and you can see the torpedo slung underneath. And they were far ahead of the British and the American technologies as far as the carrier aviation is concerned. And the outcome was their attack on the Pearl Harbor. And what the Pearl Harbor showed was the battleships that were the super dreadnoughts that was long thought to be indestructible and unsinkable were no longer so. Even up to 1941, a single super dreadnought was capable of delivering more ordnance in 1 hour than all the aircraft in the largest fleet. But the vulnerability of these battleships to air attack came as a huge shock to the navies. So you're talking of now one S curve overtaking the other. And outcome was that the mastery of these battleships overseas was over. They were eclipsed by the air power, and the carrier-based aircraft demonstrated in Pearl Harbor and subsequently the Battle of Midway that the era of the battleships was over. The reorientation in the thought process was dramatic. Because of these two demonstrations, the Battle of Pearl Harbor and the Battle of Midway, the Japanese cancelled all the battleship construction and replaced it with a new shipbuilding program centered on the aircraft carrier. The USA ordered 13 more aircraft carriers in addition to the 27 they already had. All of this just within 4 weeks of the battle. And within a very short span of a few months, the naval fleet had a completely different set of characteristics. And from being centered around the battleship, it was now transformed into being centered around the carrier battle group. The outcome was that the range over which your offensive capability increased from 23 to 25 nautical miles to 10 times more to 250 nautical miles. The critical dimension of your battle was no longer one straight line, that is the gun's range. It was now a circle. So critical dimension of naval battle got getting to define as an area instead of distance. The next technological milestone came in the form by the end of World War II. That period was the advent, heralding in of the atom bomb and the strategic nuclear warfare. And after the atom bomb was invented, and Hiroshima and Nagasaki, the first strike force, or the delivering the nuclear strike, the responsibility was entrusted to the warships. It was the carrier-based jet aircraft that were entrusted with the responsibility of nuclear strike, till the nuclear submarines came in, and then the nuclear strike responsibility was entrusted to the nuclear submarines. But otherwise, it was the warships that were at the forefront of the nuclear strike capability. The tactical nuclear weapons also came in. We talked about it during Operation Sindoor as well. And the tactical nuclear weapons also came in on board the warships. So warships had both the tactical nuclear weapons as well as the strategic nuclear weapons. But now they no longer do. But at that period, between 1955 to 1965, the warships had both of them with them. The next milestone was the weapon electronics. And we saw the radar and the sonar emerging. The sonar stories have to detect the submarines. The radars subsequently emerged. Till the World War II, the ability of warship was their ability. The firepower is what was distinguished. The design of a warship was measured by the firepower. But the ability of a ship to become aware of the existence of a threat and to be able to quickly classify that threat became to be a new way to assess the capability of the design. And this was brought in by the electronic sensors, and they brought in the battlefield transparency. And because of this battlefield transparency, for the first time, the warship was capable of night fighting, as well as ability to fight in bad weather. The first generation weapons, the weapons electronics were based on valves. They were very voluminous, very large size, and consequently, the superstructures required to be very large when you incorporated this topside electronics. Subsequently, the miniaturization of electronics resulted in topside competition between the masts to mount them as high as possible, is how that impacted the warship's design. The aircraft carrier has evolved. This was the first or the early aircraft carriers between World War I and World War II, the USS Enterprise. And this is the USS Enterprise today, one of the largest warships, displacement of 100,000 tons. And the technologies that have gone into it, a number of technologies, and all of them have climbed the S-curves that I told you, from one S-curve to the other. The catapult, initial catapult was a compressed air catapult, to the hydraulic catapult, to the steam catapult. Today we have got electromagnetic catapults. The flat top deck, the angled flight deck, so that you could simultaneously take off and land. Arrestor wires, because you had to arrest a 200 to 250 kilometer per hour aircraft, 8,000 kilos, had to be stopped within 150 meters. So you had to have the arrestor wire landing. Mirror aid landing, so that you ensure that the aircraft approaches at 3 degrees to the flight deck. Armored flight deck, so that the bombs don't pierce. And of course, the nuclear propulsion. So what the nuclear propulsion did was it did away with the need for you to be tied up to the base. You could have unlimited range and unlimited strategic mobility. So all these things were integrated into one design, and that is how today we have the modern aircraft carrier. The guided weapons came in subsequently. Now this was the era of Cold War, and the credit for the surface-to-air missiles, the surface-to-ship missiles, the cruise missiles, the pioneering work, the credit goes to the Soviet Union. We had supersonic fighter jets, supersonic bombers, but the counter to them came in the form of these missiles. And for the first time, the guided weapons gave the warships an effective defense against these high-speed jets. And what it resulted is fundamental new conditions of combat at sea, wherein you could fire your weapon from standoff distances. And deceiving these guided weapons became a means of your defense against them. And that is when you got in the ECM, that is electronic countermeasures, and the ECCM, that is electronic countermeasures, which is what we recently did in Operation Sindoor. Also, we saw that a non-kinetic way of killing the drones was through ECM and the ECCM. So this is how the new category of weapons came in, and new technologies came in that got integrated into the ships. But it had a significant impact on the design of the ships, because unlike the shells, the missiles were very bulky. So you require more storage space, more hoisting mechanisms. You require fire control systems. And when the advent of computers, the first generation computers were very large. They required electrical power, and much larger amount of electrical power. So you had to carry that much more fuel to generate power on board. And of course, you had more number of people on board to be brought in. That is the electrical and electronic engineers and technicians as well. So again, like we saw that the destroyers and frigates were not able to accommodate this additional space and volume that was required. And it was the cruisers that came to the rescue, just like cruisers were the first ones to be adapted to the aircraft carrier because of the large volume. The cruisers were the ones who took in the first generation and second generation electronics into them. And subsequently, the destroyers and frigates also increased in size in the subsequent generation of designs. So this is how the order of battle was: the guided ordnance, the guided weapons, and then the range increased to up to 500 nautical miles, which was what the circle or the concentric diameter of the aircraft's range was. The evolution of ship propulsion, the vertical steam, reciprocating steam engine to the turbine, we saw about it. Rudolf Diesel patented his diesel engine, and the robust turbo-powered diesel engine became a standard power generation capability, as well as smaller ships were powered by steam turbines. Aviation gas turbine were marinized, and we had marine gas turbines coming in to drive the propeller. And I told you about the nuclear propulsion, which gave it unlimited strategic mobility. Similarly, initial electricity on board in the 1870s were used for gun firing circuits, the subsequently AC motors and the DC motors. Electric propulsion was demonstrated as long back as 1910. British and Germans and the Americans took it further. British abandoned it. Subsequently, the concept of an all-electric ship was demonstrated in the form of submarines, when you could store electricity in the form of a battery. The power electronics, solid-state electronics, and have evolved, and today we are having electric propulsion as one of the frontline electric propulsion methods when the motor drives the propeller. The control of the battle, that is the ops room, used to have plotting tables, and used to have slow-moving aircraft and slow-moving ships to be plotted. But with fast-moving jets and missiles, these were just not capable of keeping track, and you required data automation to track the incoming targets and things. So that is when big projects were commissioned to formulate and set up the battle space management system. Today, this is what you see at the bottom is left is the Aegis fire control system, the most advanced fire control system that is fitted on the warships, all the US warships. History changed on 4th October 1957 with the launch of Sputnik and the dawn of space age. And within 7 years from the launch of the Sputnik, we had a dedicated operating satellites exclusively for the Navy called, in 1960s, the Soviets had the Navy navigation satellite system, which brought in new capability that didn't exist before: communication relays, navigation information, weather monitoring, and most importantly, radar surveillance of the oceans. Americans were caught napping. They did had to do a lot of catching up to do. And even after 10 years, they didn't have their own satellites in space. And Americans call this the Sputnik movement. And they called it the technological surprise. So this was a period of public fear and anxiety in the Western nations about the perceived technological gap between the US and the USSR. And the way to counter this one, the US came up with an organization called DARPA. It stands for Defense Advanced Research Projects Agency. It was created in 1958 in response to the Sputnik's launch. And their objective was never ever to again have a Sputnik moment. The mission was to create technological surprise for the enemy, just like the Russians created a technological surprise on the US. And most of the military technology today that we see is originating from DARPA. Whether it's internet to many other technologies have all come in from DARPA. These satellites that came in brought in transparency from the space and ocean area C3I, that is command, control, communication, and intelligence. So this is how the orbit is today, and the range has increased from 300 nautical miles about 150 years back to over 3,000 nautical miles, wherein the satellites are all connected and the data processing takes place with supercomputers and data is relayed, and this is how the battle space is controlled. The underwater battle space in the submarines, to detect them, the technologies projects were commissioned, and you had underwater sonar buoys that were kind of deployed. So the new technologies of space-based sensors revolutionized the fleet's capability, warship's capability in the form of a GPS, communication, data links between ship and shore, data links between ship and ship, tactical integration of ocean areas. And this gave rise to what we know as today as net-centric operations. That means the sensor of one ship relays the information and the weapon of another ship is able to prosecute the target. So these are called the net-centric operations. And today we have a bubble around electromagnetic space, wherein from C2 command and control, today we have C6 ISR, that is command, control, communication, computers, cybers, combat systems, intelligence, surveillance, and reconnaissance. So this have increased combat power by networking, a digital battlefield, distributed weapons and sensors. Fleet has become a system, a single system, and you're integrating the assets of land, air, sea, and space. Some example of this integration we recently saw in Operation Sindhu. So coming to the technology trends of the future, unmanned vehicles. Automation, we have seen unmanned cars coming in. So similarly, unmanned vehicles, unmanned drones. So we have got unmanned warships coming in, stealth, hypersonic missiles, anti-ship ballistic missiles, and all of them are going to require a lot of electricity. So electrical power systems are going to be required on board. So if you see this evolution, the warship is designed around its main combat offensive capability. So it used to be the cannon that became the big guns. And this is the picture that I have taken in the Imperial War Museum at London. So you can see how big these guns were when juxtaposed against the size of the 5-story, 6-story building. And then, of course, today we have the big guns have been replaced by the missiles. So what has been the impact of this evolution? Dramatic transition from brown water to blue water capabilities. Race between the offensive and defensive has continued. Today we are seeing drones and we are saying, oh my God, how will you survive the drones? But this obsolescence and again counter to that is a game that has continuously been going on. Tactical and strategic mobility, we talked about it at length. Accuracy of the main armament. We used to have only 50% of the guns that could be brought to bear, and accuracy was just about 5 to 10%. Today we are having one vertically launched missile having 95 to 98% accuracy, which is capable of 360-degree launch. These guns, big guns, used to cause a lot of recoil, and you can imagine the structural design of those ships because of this recoil. Today we are having self-propelled weapons, whether it's a torpedo or a missile, and because of that the recoil has been done away with, and the structural design of these ships has become much more simpler. So these ships are much lighter and structurally much lighter. Signature management has become the in thing today. You need to integrate, the warships have got integrated with the fleet. External appearance, but today's warships are no longer looking as menacing as the previous generation. But believe me, there are a lot of invisible features within them, whether it's stealth, whether it's software. They can't be seen. They don't have, software doesn't have weight or volume, but they are something that gives a huge capability to their ships. So the takeaways for the designer is that you need to have new capability injected, which is a mission critical imperative. And the focus should be on combining enabling technologies that work together in an innovative way to provide a ship's functionality that did not exist before. Only then you can reach a new performance plateau of a new S-curve. Second takeaway is that not all innovations have succeeded. Not all groundbreaking designs have succeeded. A number of poor designs have been produced with best of intentions, but there have been a lot of learnings from them for the next generation of designs. There's a prejudice against new ideas this is originates from the fact that there's a lot of doubt that the new technology will not really work, and it will be unreliable. And this view is often justified, and that is why the new ideas are unlikely to be dramatic, and therefore the warships evolution is going to be we are not going to be having evolutionary nature of their change. We are not going to be having revolutionary designs. So this last slide, coming to the things that what is to be remembered is that these 4 or 5 things need to combine for the warships evolution to take place. First, there needs to be recognition that value of advances in technology. Second, the advances in technology need to be combined with tactics to develop new doctrines of combat at sea. Third, very important, someone in the top management has to have the drive and determination to carry through the reform and development for absorbing and bringing this new technology into their design. The nation that commissioned the development of next generation of warship had to have deep pockets, because warship design is very costly, and it needs to be coupled with a very strong motivation of either acquiring or maintaining naval supremacy. That is where Cold Wars and the imperial things, all these things are strong motivators for this. And of course, we need to have a very strong industrial base for this to be developed. So the future shall bring in radical revision in naval roles. Either way, the key will be to make the products of such R&D to reach the fleet. And the only way this can happen is through the route of warship design. And because of this, the warships shall continue to evolve. So with this, I come to the end. I think I overstepped my time by about 5 or 10 minutes. Any questions? I'll be happy to take.
Thank you, Dr. Pramod, for giving a very comprehensive overview of the evolution of warship design. I'll open the floor for questions from the participants, but one quick question initially is, if you were to compare warship design with, say, an automotive design, evolution of an automotive design, where do you see as the key differences between the way automotive design would have evolved versus warship design? Is it because of the combat element that it would have taken, the acceleration would have been at a different rate, or what will be the key difference between these two?
I will answer this question slightly differently. Automobile is a very important comparison, but you can compare this with aviation, and you can compare this with the submarines. So you see the aviation in the 100 years where it has gone, the Wright brothers in 1910 or 1914 to 2014, where the aviation has gone. The same kind of things have not happened with underwater technologies with respect to submarines. The submarines are predate Wright brothers, but still we have not gone. So that's the challenge of the medium in which they operate. So similarly, the technological barriers that you need to overcome are higher. Similarly, warships, they operate in a very difficult environment, the marine environment, not easy and challenging. Second thing is the mass base. You will require deep pockets to be able to afford a warship. So the evolution that drives because of a very limited number of people and who can afford it and who can do that, also limits the ability to think. In contrast, the automobile has become it's no longer a luxury item. It has now become a mass common man's item. So that drives in scale, that brings down prices, that brings in automation, these kind of things. So these aspects is what the economics of it is, what has driven the evolution of the design, is what I think has been the case.
So Shyam.
Thank you, Dr. Kulkarni. Very interesting talk, very informative for me, who is not familiar with the history of naval evolution of warships. I have 2 related questions. One is that in 1962, when I joined IIT Kharagpur, uh, Kharagpur had 13 branches of engineering. And one of the 13 was
naval architecture.
Naval architecture.
Yes.
And I'm curious to know that if that department is still there, and if so, over these 60 or 70 years, what has been the output of either the department, its research, or its graduates in terms of innovations in naval architecture for merchant or naval navy ships, the warships? And have a second part of the question is, are there naval and warship technologies, any technologies which have been developed in India, which have been disseminated outside India and adopted outside India over the last 70, 80 years? Because in the recent uh, parade in China, I learned about their underwater drones, unmanned submarines. What is new in Indian warship development that we should know about? That can, yes, thank you.
So the Department of Naval Architecture is still alive, kicking, and surviving and doing well at IIT Kharagpur. They were the pioneers. Subsequently, IIT Madras set up a Department of Ocean Engineering and Naval Architecture. And outside the IIT system, it was the Cochin University who set up a Department of Naval Architecture. So primarily the naval architects who have been produced from the country, or originating from these three institutions, primarily Naval Architecture Kharagpur, thereafter Cochin University. Coming to the sir, what today we talk of Atmanirbhar Bharat and Make in India and things like that, is the Indian Navy has been at it, for the last 50, 60 years. And it was the foresight of the people in at that time. They said that with the intent that we are not going to be buyers navy, we are going to be the builders navy. So they did three things. They set up a design organization, or set up a directorate of naval design and for warship design, and then they required specialist human resources. So they entered into a specialist program and a collaborative program with IIT Kharagpur to set up these human resources. So the output from IIT Kharagpur started manning these design organizations. And subsequently, because these design organizations came up in Delhi and they were far away from Kharagpur, this shifted from IIT Kharagpur's Naval Architecture Department into IIT Delhi and embedded into the Department of Applied Mechanics. But this program is the one that has produced a pool of warship and submarine designers, who are the ones who have taken India from being a buyer's navy to the builder's navy. And today, unlike the army and unlike the other forces, we have a huge amount of indigenous shipbuilding, and we have our own corvettes, frigates, destroyers, aircraft carriers, and submarines, which are designed, not just made in India, but designed in India, and then thereafter made in India. So this has been the journey and the contribution of the naval architects from the different institutions of this one. Coming to the merchant ships, yes, the story is not as bright as that. Somehow the Indian shipbuilding industry has not kept pace with what we saw in Korea and Japan and other places. Hopefully things will change, and accordingly, the market forces is what have driven the ability of the academic institutions also to keep track of this one. Coming to the naval technologies that you saw comparing with China, I will not be able to talk about it much because that many of them fall into the realm of classified and confidential area. But believe me that some things are happening. That's all I can say.
Thank you.
I have a question for you. You mentioned how the capabilities and everything are built. If you were to design a program for chip design or any of these high tech, would you follow the model which you just described for naval architecture in building the skill base and capacity to build these new technologies, or even exploiting existing technologies which are embedded in the society? Thank you for your
Sir,
lecture. Yeah.
so I'm not really knowing much about chips and things like that, but
No,
I'm
it
just
doesn't
quoting.
matter.
I'm just
There are
quoting. I'm
chips,
just quoting.
any domain,
Yes, yes,
any engineering domain you
yes.
can pick.
So I would like to quote another famous naval officer called Commodore Paul Raj, Arugya Paul Raj, if you have heard of him, sir. He is the winner of the Marconi Medal and inventor of the 5G technology of the mobile technologies, professor in Stanford. But he's a naval officer, Indian naval officer, and he is the inventor of the first sonar. And he recently, I had an opportunity to hear him, and he talked about high tech and bringing high tech into the country and bringing high tech into the things. And what is it that you need to be different in it coming to high tech, wherein you require PhDs to be manning these spaces, and you require a huge amount of investments that need to go in, particularly in area of high tech communications or
Yeah.
chipsets or other things. You require amongst all of these things, apart from investments and apart from the technological know-how, you require policy framework, policy makers who need to understand technology. And they are the ones who will be able to catalyze the ingredients that are required for it to make it happen, whether it is technology, educational institutions, industries, investments, making the things. So when you're saying assembling a program, it requires thinking these things all together, putting a instrument that is able to cut the red tape, able to bring in both the design ability and the manufacturing ability, plus the technologies together, with the political will and the geopolitical support. So it requires a huge amount of bringing in all of this together whenever we're talking of high tech.
I understand your point, but is there something to be learned from the evolution of naval architecture and naval engineering in India as a model of a way to think about future technologies we want to indulge in?
Sir, the takeaways that I can submit for consideration is that we need to build institutions. We need to build institutions, and we need to build capabilities in those institutions, and we need to fund them continuously with for them to come up with subsequent generations of designs. And we should not close the tap. We should keep on, and there's a lot of learnings and a lot of institutional knowledge that gets created. There's no failure in a design. You only learn how to design it differently. So this kind of a hand holding and support is essential for sustaining these things. Definitely. And of course, the market forces need to be created. You can't survive a shipbuilding industry only on naval orders. We require commercial shipbuilding also to take on and create an ecosystem. That is how Chinese shipbuilding has increased. Today, they are able to have strong military shipbuilding only because it is ridden on their very strong merchant shipbuilding capability. So if you don't have a strong merchant shipbuilding capability, you can't have a very strong cutting edge warship building capability.
Thank you very much. It was a very interesting talk. We invite you to come back and give any other lecture related to this area, but you have also talked about modern systems engineering. What is systems engineering from your perspective as a practitioner would be very, very useful to this group, I think. And we invite you to, I don't want to take too much time, maybe others have questions, is that we invite you to come back as many times as you want to talk about your experience, because life experience is very important to be conveyed to younger engineers who are growing up today.
Yes, I shall certainly take it as a privilege to be made this offer, and I shall think about what can be the more suitable topic once again.
And possibly bring other colleagues to come and speak in our series.
Yes, sir.
Yeah, we really feel that our engineering students don't get exposed to people with practice and the insight from wisdom and insight coming from practice. You can learn skills, you can learn knowledge, but you cannot learn wisdom without lived experience. And I think we need to connect that to our engineers today.
Absolutely. Absolutely. And that is what has been motivating for me to come back to an educational institution, sir, though I could have gone into the industry as well. But what you just now mentioned is what is the very strong motivator for me. And that's how I'm collaborating with Dr. Varadarajan as well to try to make a small little, impact or influence to bring this into the education system.
Anyone else has any question? You can please unmute and ask.
Good evening, sir. I have a small question for Dr. Kulkarni. Sir, first of all, thank you for the wonderful presentation, and we totally got engrossed in your in the whole evolution of warships. What I feel is that this evolution of warships is totally an integration of electronics and communication, electrical engineering, mechanical engineering, and CSC. So from today's perspective, how do you view artificial intelligence to further bring in evolution in the warships?
Yeah, see, it is the few disciplines you mentioned. Warship is an amalgamation, and it takes many more disciplines to make a warship to emerge. And the naval architect is a sutradhar who basically brings in all of these things. Material science, it is all of it. But this AI is something that is going to completely transform and change the things in the future. But there's lot of papers that I'm coming across who are applying AI, particularly in the initial design and initial part of the design, or one click of a button is able to come up with a design. But the CAD, then it came up, the CAD, the A in that was computer assisted or computer aided design. So we have to always remember that these tools are always to be used to aid design. They are not to be replacing the designer. So even the artificial intelligence, when it comes in, it can be used for providing you some tools and providing you some inputs and but it should not, and it will not replace the designer. If that does happen, then the designer is going to lose the ability and the capability of how to undertake the design, because the nuances of so many cross-functional implications of every act of commission and omission is something that to be acquired by doing it hands-on or acquiring the things. Artificial intelligence, if it does it, even if it is capable of doing it, we're going to be completely losing this art of the ship design.
Thank you so much, sir. Thank you so much. But it will be always a co-design, as you mentioned, that software part is what AI can assist more in that part.
Yeah.
And the hardware always remains related to the other fields, and that is how a co-design of these things will be useful for the overall, I think.
The one place where I can see a lot of application of that one is typically like how the architects use it. You have got a building space, and the layout of the various rooms within the building, that building is, the AI is generating some 300 different permutations, combinations of the layout of a building. So we are having 300 to 500 compartments on a ship. So I myself am working on a project of applying AI for generative AI for developing the general arrangement of a ship. But however, so these are very useful tools, but I use that word A in CAD. It is assisted or aided tool. You got, computer aided or artificial intelligence aided design. So these are the kind of how it will be.
Thank you so much, and thank you to Professor Varadarajan also, because of whom we could interact with you today. Thank you so much.
Thank you.
So this is Professor B.K. Roy from NIT Silchar.
Yes, sir.
Sir, I have first a comment. Your presentation is good. That is already been said, but I like your slides very, very, very much. Your slides were extremely good, sir.
Thank you,
very
sir.
happy to see the slides. Sir, finally, I wish you to rate, what is the current status of our warship with the available warship in a scale of 10. So that we just, I don't want you to disclose any confidential information. Just in a scale of 10, if you can rate, sir, our warship with respect to available warship in a scale of 10, sir.
Sir, what I'm saying could be a little dated by a few years, but I had come across the top 10 warships. If you search on Google, that that kind of thing, the ratings, top 10 warships. So at that point in time, I'm talking a few years ago, I did have 2 Indian designs in the top 10. And this is something other Google search or that kind of a thing. So I think that I have not done this recently, but if you do, I'm sure you will find at least one of the Indian designs to be there in the top 10 frigates or in the top 10 destroyers. So we may not be there absolutely in the top things, but we certainly are there. The reason being that the naval, we have mastered the naval architecture, we have mastered the integration, but the challenge really is about the weapon systems, and we are having overcome that. We have a lot of good indigenous weapon systems with us. So it's an integration of all of this that gives them the capability. The cutting edge is really in advance. These things have happened is the stealth. And stealth technology is something that is, people keep very close to their heart. It keeps, they don't share it. So these are the combinations of these capabilities is what creates a ship. But I recommend if you can search this. And what I did a few years back, top 10 frigates, Indian ships. You might like to do that today and see. You might find some Indian ships in the top 10.
Thank you, sir. Thank you.
Yes.
Thank you. One last question. Maybe if anyone else has one last question, we can take.
I just wanted to make a remark. Well, first of all, thank you very much for a wonderful lecture. And I think one of the important things I learned from your lecture is this. If we have a certain amount of will and the ability to build the workforce to do it, we can achieve what we want.
Yes, yes.
But we are not able to do that in disciplines across the board in our system. And that is one thing. The other thing is, of course, the separation of theory and practice in the institutions. So I have a lot of other things to tell you about, including the layout problem, because I had worked on one long time ago. I will contact you and then we can connect about those things, because my primary area is supporting systems engineering through computational and cognitive means. So it is relevant to the previous question, because AI is individualistic, but systems engineering is a collective intelligence.
Exactly.
It cannot be replaced by AI. So we need to pay attention to the notion of collective intelligence if we want to build the capabilities and capacities to do the kind of technological advances we want to make. And I think your lecture illustrated that very beautifully.
Yes.
Thank you very much.
Thank you, sir. Sir, I would first of all thank you for the positive remarks and comments, greatly encouraged. I do not have the names and details of everybody who was connected up. I request Dr. Varadarajan if I can have it, and I would like to connect up with all the people. The very fact that you are in this forum, that you're interested in design, I would also be greatly benefited, and when I engage with you, I would like to reach out to you. And certainly, sir, I'll reach out to you for more inputs on this subject of systems engineering. Thank you.
We'll do that. So thank you very much, Dr. Kulkarni, for sparing your time and speaking to us. And also thanks to all the participants for joining this talk. We will shortly announce the next talk. Most likely it will be in 2 weeks' time, typically on Wednesdays. So we will get back to you with the next announcement shortly. So thank you again, all of you, for joining today's talk.
This video will be online.
Yes. Yeah.
Thank you, Pramod. Thank you, Sudhir.
Yeah. Thank you, sir.
Thank you.
Sir.